When you look out at the ocean, it doesn't necessarily look like it's doing very much, but it's a vast, dynamic system. Tell me about your view of the ocean.
Well, the ocean is really a fundamental, has a fundamental influence on the Earth's climate. I mean, from global to regional scales, they can store, transport, and exchange with the atmosphere a huge amount of heat, water, gases such as carbon dioxide. And we know, for instance, that over the past 50 years, they absorbed more than 90% of the extra heat gained by the Earth due to global warming. This is an extremely important role of the ocean as a whole to regulate the climate. This is also due to the very large heat capacity of the ocean, which is more than 1,000 times the one from the atmosphere. So this really shows the importance of the ocean. But the oceans, they do not only store a huge amount of heat, they transport them over a very long distance through ocean current. This is really the dynamic part. Actually, it is really the interplay between ocean dynamics and this heat storage that regulate our climates and that also affect the regional climates in the world.
Now we've got a wonderful toy here, which is a picture of the globe that we can move around. And tell me about the black bits of the continents. Tell me what the colour of the ocean here is showing.
Yeah, the colour represents the temperature of the ocean, and we see that the temperature, depends on latitude because the oceans are gaining more heat in the tropical, subtropical.
So here, this
in
red
this
bit,
place, you see there's a lot of heat going. But then we have a really important contribution of the ocean that redistributes through the ocean current this heat, which is stored in the tropical, subtropical region towards the high latitude. And this is part of what we call this thermohaline circulation, which is a fundamental component of the ocean circulation. And the idea is that we have current moving northwards, which carries this warm water towards high latitude. So when they move northwards, they lose heat and they warm the atmosphere. So this is very important effect to regulate the climate. But the water also gets denser because colder water are denser. So when they arrive to the high latitude in those regions, water are very cold. They can be also saltier because when you have sea ice formation, you have more salt in the data. So they are much more denser, so they can sink. And actually they sink to depths of up to several thousand meters. So they sink and then they flow back very slowly in the ocean interior and they fill the ocean basin. So we have this kind of overturning circulation, which is fundamental to regulate the climate, and which is very important parameters that we oceanographers want to follow. And why we want to follow it? It's we know from the past, the analysis of past sediment, of ice core, they show that in the past we have had a rapid variation of this meridional overturning circulation over several decades only. And this was associated with very important change of our climate. So this is the reason why we're really carefully monitoring this meridional overturning circulation from in situ observation, from satellites, and from model.
So we can see here, let's go back to the detail a little bit. The reason for this bright red patch near the equator is that the sun's energy is being absorbed and it's being taken up by the ocean. Yeah.
Exactly, but this part of the ocean cannot warm indefinitely. So you accumulate water, you accumulate heat, but this needs to be transported towards the high latitude. It's done by the ocean and by the atmosphere, but the ocean has a fundamental role through this overturning circulation.
So this is about energy distribution, not just around the oceans, but into the atmosphere as well.
A very, essential, which is that people do not often realize, it's how important is the ocean for the energy of the planet. And I was mentioning before the fact that the ocean has absorbed 90% of the Earth's warming over the last 50 years, which is Earth warming, which is due to this increase of greenhouse gas concentration. But this shows that really the ocean, through the heat absorption, is a major driver of the energy system of the Earth. This is a fundamental, and without the ocean, it would be this planet we couldn't live in this planet.
I think of the oceans as an engine. They're shunting heat around, and it's an enormous amount of heat, and it's redistributed around. And so that means there are currents, because that's what we call moving water. How can a satellite help you with understanding currents?
Well, actually, satellites provide essential observation to monitor the ocean circulations on our different types of satellites. But the most important one for monitoring the ocean circulation are satellite altimeters. Altimeters can provide measurement of sea level variation, and we know that sea level is directly related to ocean current through the geostrophic approximation. So sea level slope is associated to a current. So thanks to satellite altimeter, we can map the sea level globally, and from the slope of sea level we can derive ocean current. So this was actually a revolution in our way to observe the ocean from space, thanks to the satellite altimeter. We also know that we need several of them, because we know that we need to observe the ocean at high resolution, because we have a lot of fine-scale structure which are very important to understand the dynamic of the ocean. And this is the reason why we actually have several altimeters flying. So we have one reference mission for climate application with the JSON series, and later on with the Sentinel-6 satellite from the Copernicus program. And we have, for the present time, the Sentinel-3 altimeter, which are essential to provide complementary sampling and to monitor this ocean at very fine scale.
So by using satellite altimeters, you can monitor the shape of the ocean surface, because it's not completely flat everywhere. It's got lumps and bumps, and they can tell you where the currents are.
Yeah, exactly. If you flow over the Gulf Stream, for instance, you will see a sea level slope of about 1 meter over several hundred of kilometers. And this slope is directly related to the current. So it just is very similar to what you have in the atmosphere with the low and highs and the winds around this. This is exactly the same phenomena. This shows really the strong value of altimeter and sea level measurement. It's not only for sea level. Sea level is very important, of course, for climate, but you can really get the ocean current. In addition, we have other satellites that provide a sea surface temperature observation, ocean color, and we also know that this, at fine scale, the variation of sea surface temperature and the evolution over time, they also reflect the ocean current, because the structure are advected by ocean current. So if you follow a sea surface temperature map from a satellite over time, you can derive ocean current. We also have very important satellite observations that are quite important for ocean circulation studies as well, are the observation from wind. Because we know that wind is the main driver of the ocean circulation, and we can monitor wind from space as well through scatterometer mission. This is very important observation from space for ocean circulation studies.
We have these different size scales then. We have this very large overturning, which is due to heat redistribution. And then I think we've got a map here of some ocean currents. Suddenly, when you can map these ocean currents, suddenly there's detail everywhere. Tell me about what we can see here. Yeah,
actually there are a lot of details, and it's often when we represent this ocean circulation, this great ocean conveyor belt, so thermal line circulation, it's fine, but it's a very crude approximation on how the ocean works. It can actually be misleading for some aspects, because we know that fundamentally the ocean is a turbulent system. And its circulation, the currents, they are fed with a lot of eddy, meanders, filament, fronts, and so on. So this is what we call the mesoscale variability. So it's much more complex than the visions you would get with the great ocean conveyor belt. If you look at current from the Gulf Stream here, you will see that it has a lot of meanders. Those meanders will shed eddies. Eddies will have filament, fine scale structure. And you could say, okay, it's not important for climate. Maybe we need the big picture with a large scale. In practice, we know that even those small scale, they are important if we want to understand the role of the ocean on climate. And of course, it's also very important for many other applications, such as what we do, for instance, with the Copernicus Marine Service. We are using satellite altimeters together with other satellites and in-situ observation to analyze and predict ocean currents. This is very important for climate application and so on, but it's also very important for a lot of practical applications, ship routing, helping the offshore operation. If you want also to predict the fate of marine pollutants, you need ocean currents at high resolution. So there are many requirements for this satellite observation, but is satellite observation alone will never do the job. So they need to be complemented by in-situ observation to monitor the ocean interior and models to provide analysis and forecasts.